All right, so continuing from yesterday, we're looking at some first fundamental theorem stuff. I want to wrap that up, and then I want to show you the second fundamental theorem. Okay, so like for this, I know you don't have to memorize an awful lot of antiderivatives because you just reverse reverse derivatives, right? This is one where you can just kind of think in reverse. I mean, what's the antiderivative of secant x tangent x? Just play calculus Jeopardy with that. What would you differentiate to get that? Secant, yeah. Mm-hmm. Right, so this would just be secant x from 0 to pi 6. And secant, like I would just think of secant as 1 over cosine. I would never in a million years remember what it is for secant, but I would think like this. And so what's that going to give me? Cosine of pi 6. So you can do this quickly if you just think about pi 6 is going to be the smallest angle in quadrant 1, right? So at pi 6, you're going to have big X, small y, right? And what are the numbers you see on the unit circle in order? They go 0 is the smallest, 1/2, square root of 2 over 2, square root of 3 over 2, 1, right? What do you know? Which ones go together? Well, those two go together, these two go together, and those two go together, right? Does that make sense? And so this would be the one where it's got to be small, big, right? Not 0, 1, that would just be on the axes, but for a point that's not on one of the coordinate axes, it would be, so it'd be square root of 3 over 2. And then cosine is 0. So it'd be the reverse of that, though, wouldn't it? 2 over the square root of 3. Which is 2 radical 3 over 3 if we rationalize the denominator. And then cosine 0 would just be 1, right? So we could write it like that if we wanted to. Does that make sense? Okay, good. All right, how about that guy? E to the x is another one that's easy, right? What would be the antiderivative of e to the x? E to the x, right? What's e to the log 9? 9, right? Because the e and the log would cancel, right? And then e to the 0? Anything to the 0? 1. Okay, good. All right. Okay, this is one we got to take a look at. Okay, so this is not one, there isn't hey, guys in the back, you guys got to keep it down just a little bit in the back, just a little bit, 1 notch. There isn't, you'd think this would be a power rule, right? Because you'd think of this as 4x to the minus 1, okay? But if you play the power rule game with an antiderivative, that would tell you 4x to the 0 divided by 0, right? See what I'm saying? Because like normally we would add 1 to the exponent and then divide by that. So that doesn't work. You can't divide by 0, and obviously it's not constant. So this is one that kind of falls through the cracks. So we need to come up with this one. I mean, can you think of what it would be? So it is a log, yeah. Okay, how can you show that? Well, here's a way you can always come up with with derivatives, derivative formulas, or sorry, antiderivative formulas based on the original derivative, right? So you'd have to kind of think in reverse here a little bit, because you know that the derivative is going to give you 1 over x, and the 4 we would just pull out front, right? That's just a constant, but we'll deal with the 1 over x part. And let's be more general than that. Let's just deal with it like a u. So we could say something like this. We know the derivative like if we, the derivative of with respect to x of log u is equal to 1 over u du dx, right? Okay, everybody agree that's the corresponding derivative that's going to give us a 1 over x in this case, but in general a 1 over u, right? Okay, so how do we go from there to there? Well, what we're going to do is the rigorous steps would be we're going to solve this differential equation. So first thing we would do is we would multiply each side through by dx to put this in write this derivative in differential form. We don't need the dx's in there in this case, right? The argument of our function is a u. So then we'd get the derivative of log u equals 1 over u du. Okay, how do you undo a derivative? You take an antiderivative, right? So the next step would be to do this. We're going to take the antiderivative of both sides, and an antiderivative is going to cancel the derivative to within a constant, right? If we undo a derivative, we know that it cancels this, but differentiating a constant, the derivative of a constant goes to 0. So we know that we're going to have to add a plus c there. So we end up with log of absolute value of u plus c is equal to the antiderivative of du over u, or 1 over u du. We'll just call it du over u. How about? Flip that around, and there's our antiderivative. Okay? So we end up with antiderivative of du over u equals log u plus c. Now we attach absolute value bars to the u there because we might have a situation where, like if we'd have limits of integration, let's say, where u could be negative, or in this case x could be negative, right? Like we could have done this from -9 to -1, and that's a function that's defined for negative numbers, right? The inverse function, negative values are in its domain, right? The only number that's not in the domain of the inverse function 1 over x, reciprocal function 1 over x, is 0, right? So because we can have negative numbers in the domain of this function, but we can't have negative numbers in the domain of our log function, we've got to place absolute value bars around the argument of the log. So this is what would show up in a table of integrals. Okay? Does that make sense? Okay? So how would we go about this? Then we would just say we're going to pull the 4 out front, and then we've got the integral of dx over x from 1 to 9. So that's going to give us 4 times the antiderivative of 1 over x dx is just log u. Now we don't include the c, right, if we're doing a definite integral. And why wouldn't we include the c? Seems like it ought to be there, but if it were there, we're just going to be subtracting it from itself, right? If I had the plus c there, I would just end up with, I'd end up with log 9 plus c minus log 1 plus c. So the c's are always going to cancel. So we just never include them, right? Do I need the absolute value bars? That should be an X, not a U. Do I need the absolute value bars in this example? They show up here. Do I need to put the absolute value bars around the X there? You're right. How come, Madeline? Yeah, because we're evaluating it over positive limits of integration anyway, so we don't need an absolute value. So we just end up with then 4 times log 9 minus log 1. And what's log 1? 0. How can you know? Because you just flip that around. Your log is an exponent. That's like log of 1 is equal to, if we say log 1 is equal to z, just call it something, right? Call it z. Then that's a base e, right? So that's saying e to what power equals 1? 0. Make sense? Okay. So that's 0. What about log 9? I mean, we can't come up with an exact value of that, but could we simplify it a little bit? Being as 9 is a perfect square. We always like to write logs in terms of the smallest log possible. So it'd be the log of 3 squared. What's the log of 3 squared? Right? Yeah, 2 log 3, right? We get 4 log 3 squared, which is 4 times 2 log 3. So we just get 8 log 3. Why is that better? It just is. We just like to plug the smallest numbers into log possible. Okay. Give me thumbs on that. We good? Okay. Didn't we do that one? Oh, we did. Okay, I can get rid of that, can't I? Yeah. Okay, next issue, mean value theorem for integrals. So let's quickly review. We already did a mean value theorem, right? We did a mean value theorem for derivatives, right? That went along with Raleigh's theorem. Let's review that real quick. So the mean value theorem for derivatives, you guys remember what that was? Mean means average, right? So what did this say? If we had mean value theorem for derivatives said if we have a function that is continuous and differentiable, right? So it's got no sharp corners and it's continuous, meaning it's a smooth function. Whenever you hear continuous plus differentiable, it means it's smooth, okay? Smooth function. And if we look at this on an interval from A to B, remember what this said? This said that there has to be at least one place on the interval, on the open interval from A to B, so between A and B, where the slope of the function equals the slope of the secant. Connecting the endpoints, right? So where the instantaneous rate of change equals the average rate of change. That makes sense? Okay, we know there's got to be at least one place where that happens. And it looks like in this case, it would be about there. And so we would call that value C. Okay? So again, this is an existence theorem. It just tells us that if you meet these criteria, then there exists something interesting. And here's the something interesting. So if F is a continuous on A to B, and it's differentiable on the open interval. Okay, so between the endpoints, if it's differentiable, remember all that means is it's smooth. And that really is a math word, smooth. Then there exists at least one C such that f prime of C equals, how would I say the slope of the secant line? It's just the difference quotient, right? That's how we always define the slope of a secant line. This, remember, this function is f. Just rise over run. How would I say that? There you go. F of b minus f of a over b minus a, right? Remember that stuff? And then how would I find it? Well, just use algebra, right? We would just calculate the derivative, and we would set the derivative equal to whatever number that was and just solve, right? Solve that equation. And the solutions, all of the solutions that lie between a and b would be the values we're looking for, okay? We'll review that later. I mean, you remember doing that kind of vaguely, though? Okay. So the mean value theorem for integrals just does something similar. Mean value theorem for integrals just says if I've got, well, let's look at the conditions here. If f is doesn't even have to be differentiable. If a function is continuous over a closed interval, a to b, then there's going to be at least one point, interior point C. So this is a little mistake. I took this from the OpenStax book, and there are sometimes mistakes in there. So this should be 1 point C on the open interval. So between the endpoints, such that the average value of the function is such that the function has its average value, okay? And what do we mean by its average value here? We have to define that. What's the average value of the function mean? It means, here's a way to think about it. So I've got this purple function, and I'm looking at it on the interval from a to b. So it's easier to visualize if I take out my two-dimensional grinder and I come up to the board and I'm just going to grind this thing down into rubble until I can reconfigure the curve so it's got a flat, so it's got a horizontal, it's defined by a horizontal line, right? So as I grind this thing down, the area is going to crumble down and fill that little divot. And as soon as I can't grind anymore, as soon as I can't, as soon as I've ground this thing down and there's no place for stuff to go, it can't reconfigure anymore, then I've turned it into its average, right? So the average, I'm taking the area under the purple curve. In other words, I'm taking the area under the purple curve and I'm reconfiguring it into a rectangle which has the same width as the purple interval does, but now it just becomes a rectangle, so it's got a constant value the whole time, right? A good analogy for this would be thinking about something like, say, velocity. Say we were graphing, instead of y, say we were graphing v of t as a function of time. Okay, if I were doing that, this would be a situation where, like, I'm starting off at, say, 60 miles an hour, and I'm increasing my velocity a whole bunch, and then I'm going to slow down and go slower for a while, and then I get to the end. Well, the area under a velocity time graph is displacement, right? We haven't really talked about that a lot, but we will. So the area under a velocity time graph is displacement. So that's going to tell you how far you traveled over that course of that trip. Well, I could instead of like speeding up and slowing down, what if I just put my car on cruise control the whole time? And I set the cruise control so I would end up going the same distance in that amount of time, right? Well, how would I get that? I would just take the total area divided by the width. Wouldn't that just give me the height of that rectangle? Anybody get that? Okay, so that's how we're going to do this. What we're saying is this part right here essentially is saying the area under the purple curve. What's this part saying right here? Well, this is saying the area under the red, or whatever color that was originally, the red rectangle. And we would just say that whatever the height of that is, we're going to call that f of c, right? So the area of the red rectangle is just the height f of c times the width b minus a, right? Make sense? Okay. And so if I want to calculate the average value then, well, if I'm setting up this height so that those two areas are equal, I could just solve for f of c, right? Wouldn't the area under the red rectangle just be the total area, which is the same thing as the integral? We just defined it that way, right? Blue area and red area are the same, but this is a calculable area because we presumably know the function and we know the limits, right? So the area divided by the width should give me the height of the rectangle, shouldn't it? So therefore, the average value, f of c, just equals the total area divided by the width of the area. Okay, give me 1 to 5. Does that make sense? Okay. Okay, I'm not seeing 5s though. So what's not clear about that? Ask a question. So the average value is defined as, well, and it's, what's interesting about it is, I mean, how would you define an average here, right? Because you're going to spend a certain amount of time. Do you necessarily spend half of this time when we're driving above the average and half below? Not really, because the faster you're going, the more displacement you're contributing while you're going faster. So it's kind of a weighted average in a way, right? I could also draw a situation where we did something like this, right? Like what if our graph looked like something like that, and I'm looking on the interval from A to B, right? So there's the interval. Well, if I ground this thing down, my average might look something like this value maybe right there. Agreed? So I may spend most of the time going slower than my average speed because when I was going faster, I was going a lot faster, right? You get the idea? Okay? So it's a weighted average in that sense. It's an area average is what it is. Okay? So again, we're just asking what would be, if I were to take this area as, and write it as in the form of a rectangle, so it's going to be its average value times its width, what would that average value have to be so that the areas were equal? Because in calculus, when we're taking integrals, the area under the curve has some real significance. That's what we're trying to find. Could be work done in physics. It could be total energy in physics, whatever it is, right? If we want to find the average, well, we're just going to smear out that total value divided by the width of the interval over which we're calculating it. Does that help? Okay. So here's an example of some problems, right? And here's what I just stated, I guess, right? That's how we would calculate the average value from our mean value theorem, okay? So it says find the average value of this function on the interval from -2 to 2. That's pretty cool that we can do that, right? How are you going to find an average value? And think what an average actually means. Like if you're averaging a bunch of numbers, what are you doing? You're adding the numbers up and dividing by the number of numbers, aren't you? So would you agree that if I added up the numbers like 3, 4, 5, 6, and 100, that 100 is going to skew that average up quite a bit, isn't it? Just like this high peak skewed that average, right? Really, if you're adding numbers, that's kind of the same thing as what you're doing here. You're just adding pieces, only this time it's pieces of area instead of just numbers. And you're dividing by the width of the area is equivalent to the number of numbers. Okay? So, what are we going to get here? We want to find the average value. Well, it's just going to be the area under that function divided by what number? 4, right? 2 minus negative 2. Okay, so let's do it in yellow. So we're going to do the integral of 4 minus x squared from negative 2 to 2. There's our total area divided by 2 minus negative 2. Okay, well, on the top, what's that antiderivative? Four x squared, or sorry, 4x, right? No, 4x, right? Minus x cubed over 3. From negative 2 to 2, okay? What do you notice about those limits? They're symmetrical, right? Okay. The limits are symmetrical. And so I could, at least in my head, I could break this up into separate integrals that I'm evaluating over the two pieces, right? The two terms I could break up into separate integrals. I could integrate term by term over these symmetric limits. And what am I going to find? I've got 4x evaluated from negative 2 to 2 minus x cubed over 3 evaluated from negative 2 to 2, all divided by 4. What's interesting about that? Yeah, it goes to 0. In fact, I was thinking in this case that one of those was going to be even, so I didn't even really have to do that, honestly, because I can see this whole function is odd. I didn't even need to do that stuff, right? Everybody get that? Because how do I know that's odd? Because it's a polynomial with only odd exponents. So if I apply the test for odd functions to that, it's guaranteed. I mean, it's going to show up. It's going to be true that it's odd. Okay? So if I integrate an odd function over symmetric limits, the answer is 0, right? So this actually is a pretty easy integral to do. I just get 0. Okay? So that's the average value. We did that. The average value is 0. Now part B wants to know, where does the function equal its average value? That's a non-calculus question, right? That's a pre-calculus question. I'm just going to set the function equal to 0 and solve. Okay? So if we do that, where does, so for part B, where does the function equal its average? And does 4 minus x squared equals 0? Well, that's going to be when x squared equals 4, right? So what does x equal? Two and negative 2. Oh, you know what we didn't do, though? Oh, no, that's right. There's the function. Oh, the average, yeah, what the heck? Huh. Okay, let's look at this on a graph for a second. Yeah, that's weird. What the heck? That's not what I was expecting. Maybe that's what it looks like, but it just doesn't seem right to me. 4 minus x squared. Oh, no wonder. God, what am I doing? Jeez, that was stupid. The function, was the function odd? Was the function odd? No, the function's even, right? We were looking at I was looking at the antiderivative. We don't care if the antiderivative's odd. We care if the function's odd or even. The function is even, isn't it, right? So this shouldn't have been equal to 0. God, that was really stupid. What's our rule for integrating an even function over symmetric limits? Duh. 2 times the function evaluated from 0 to one of the limits, to the upper limit, right? So this should have been, let's fix this. I can get rid of all this stuff. And get rid of that stuff for now too, why not? What this should have equaled then is 1/4 times 4x minus x cubed over 3. We'll take the whole thing and multiply by 2 and just go from 0 to 2, right? Right, we're just going to double the area from 0 to 2. Everybody get that? Okay. So that makes sense? We would have just taken 2 times the original integral. I guess I should probably write that down too. I mean, we already did the antiderivative. I'll write it down. I don't want to skip steps. Then the notes will be all messed up. So we probably should have written it this way. It's going to equal 2 times the integral from 0 to 2, right? And we should have seen this before I even took the antiderivative, right? There was no need for us to take we would have seen this right away, that this is an even function over symmetric limits. So there's the antiderivative. Okay. Right. And we're dividing that by 4. So I'll just put the 4 out front, right? And so we get 1/2 times this. At 0, that's all going to go away, isn't it? Right. So really, this is then just equal to 1/2 times, at 2, I'm going to get 8 minus 8/3, so 16/3. So 8/3 is my final answer, 1/2 of 16/3. That all look right? Check my work. I seem to be making lots of mistakes today. Does that all seem right? Right. What did we really do here? All we did with this, did we have to do this? We didn't have to do this. But we just made a trade. We just said, okay, well, we see that we've got up here, pick a different color, we've got that integral, because it's over symmetric limits, we could trade for that integral, right? Everybody get that? Okay. So now we got to go back and ask for part B, where does the function have its average value? Okay, so where does 4 minus x squared equal 8/3. You know, we'll just isolate the x squared and square root both sides. So we'd end up with x squared, push that to that side, x squared equals 4/3. So x equals plus or minus the 2 over the square root of 3. Does that make sense? And that looks about right, doesn't it? If we look at this function, if we graph this thing, f of x equals, what was it, 4 minus x squared? There's our function. If we're only looking between -2 and 2, we said that it has its average value of what? The average value is 8/3. It has that at plus or minus 2 over radical 3. Okay, so let's graph this other function here. Let's graph the function y equals 8/3. And I bet you that -1.155 and positive 1.55 are 2 divided by the square root of 3. Let's just check it. Yeah, makes sense? Okay, so those are the places where the function has its average value on that. Say it again. That's a good question. I bet you can add up area. You might be able to do areas. Ah, look at that. You can. So this is, okay, this is kind of cool. So we could do then, okay, let's do this. Let's do the integral. I wonder what, like if I do int, yeah, okay, you just type in int and it does a definite integral. Okay, so the definite integral from -2 to 2 of f of x, I've already defined f of x, dx is that. Wow, that's pretty cool. Isn't that what we got? I mean, if we turn that, oh, that's not what we got. What did we get? Oh, we did area divided by 4, which is 8/3, right? We didn't do area. We did average value, right? Make sense? Okay, so we did it right. And then instead of calling this y, let's call it g of x. So I could do the same thing down here. I could do the integral from -2 to 2 of g of x dx. And what do you know? Pretty cool. Okay. I wonder if there's a way to like show that as an area, like to actually fill in the area. I know there is because I've done this before. I can't remember how to do it though. I know there is. Okay, I know there is because that's what I did. It has to be what I did. Well, it goes back a couple lectures ago, but